Within recent months, the Atomic Energy Commission and the Department of Defense have conducted important tests of an experimental device based on the thermonuclear principle, leading to the development of a very large yield weapon. In addition, a proof test was made of a large yield fission weapon. These constituted Operation Ivy. The report of these accomplishments is about to be presented in film form. We will show you new techniques and new scientific developments. We will minimize the portrayal of normal military service support, since you are familiar with this aspect of test operations. As commander of Joint Task Force 132, I invite you to observe Operation Ivy, carried out on our Pacific Proving Ground, Eniwetok Atoll.
If it wasn't a big one.
Captain, we're in position. Recommend reduce speed, sir.
Very well, Mr. Adams. Helmsman, steady as you go. Steady as you go, sir. All engines ahead 1/3.
All engines ahead 1/3, sir. Engine room con ahead 1/3. All engines answer ahead 1/3, sir. Engine room reports making turns for 4 knots, sir.
Very well. How are the wind and tide affecting us?
As predicted, sir.
Good. It's important that we stay within that area so we remain within the television cone.
Yes, sir.
Welcome aboard the USS Estes. As you may or may not know, the Estes here is the command ship of Joint Task Force 132. We have minutes to go before the first blast, mic shot, of Operation Ivy. 59 minutes now, to be exact. We've been here since daybreak. Left Weetalk last night during the early morning hours. Now, as you can imagine, feeling is running pretty high about now, and there's reason for it. If everything goes according to plan, we'll soon see the largest explosion ever set off on the face of the Earth. That is, the largest that we know of. Some 8,000 men will view the event from this point. Oh, by the way, the carrier over there is the Rendova. She's primarily set up as a base for fighter security and helicopter reentry. And that's the Curtis over here, the weapons assembly ship. In the time between now and H-hour, I'd like to show you around, if I may, and introduce you to some of the people connected with this operation, and in general, piece together the events which have brought us to this point. To start off, I'd like to show you something over here. You realize there are many miles of ocean between us and Eniwetok Atoll. To know what's going on back at the atoll, these antennas are receiving televised signals and are giving our men here a second-by-second account of what's happening on Shot Island. The television receivers are in here, in the control room. Oh, but before going inside, let's take a look at a chart. It may give you a better idea of our location. This is our position. 10 miles south of Elugelab Island, or about 30 miles south of Elugelab, the shot island. We must keep a very accurate position here because of the televised signal. It's a very narrow beam, and the ship must stay within that beam. Now, perhaps you're wondering why we're out here in ships. Well, the answer is very simple. It's too dangerous on land. We're expecting a yield of from 4,000 to 10,000 kilotons. That's equal to between 4 and 10 million tons of high explosives. Considering all possible effects from a bang of this size, the best observation point is at sea, on a mobile platform at a known safe distance from 0 point. Okay, let's go inside now. Well, this is it. This is the control room. I'd like to have you meet Mr. Stan Burris, the commander of the scientific task group. Oh, Stan, I wonder if you could tell us something about the operations that go on in this room.
Sure, I'd be glad to. The screens you see in front of you enable us to monitor the timing and firing system and the cryogenic system. The lights indicate that the timing signals are functioning properly. The dials, this collection of dials, indicates that the liquid deuterium is in the proper state for firing. If you will look close, you will see that it is now 55 minutes before H hour. As time clicks off, more and more lights come into operation. This is the 1 minute light, 30 second, 15, 5, 1 through firing. Since this is a thermonuclear test, we are using a type of hydrogen in a liquid state. It is necessary to keep a close check on the condition of this fuel. The hydrogen is not in the proper state or at the proper level. It would have such a marked effect on the results that there is no point in continuing the experiment, in which case we would postpone the shot. Is there any chance of that so far, Bob?
No, there isn't, Stan. The cryogenic system has been operating perfectly for several days, and we're not particularly worried now.
That's fine. I have here a layout you may be interested in. This diagram will give you a general idea of the whole setup. Data from the sequence timer is piped over to a display panel. Likewise, cryogenics data is piped over to this display panel. This kind of display panel is new to atomic test work because of the large number of remote control and metering problems encountered in this operation. For one thing, the master timing and metering apparatus is located next door to the shot cab, rather than being placed some 20 miles away on Parry Island, as is usually done. This close view is possible, of course, because the lens of a television camera, rather than human eyes, is watching events. So cryogenics data piped direct from Mike and information from the sequence timer is transmitted from the small building attached to the main cab and is relayed by way of a TV antenna atop a 375-foot tower to the Estes.
So that's the flow. From timer on through to display panel, cryogenics data to panel, picked up by a television camera and relayed on out to the Estes. A very ingenious arrangement. But what happens if you have to stop the firing mechanism, or can you stop it?
We can stop it all right if we have to. We have a radio link direct to the firing panel in the shot cab. If we have to stop the shot, we simply push this button.
Just a simple flip of the wrist, huh?
That's right, but a lot of work goes down the drain. You understand, we don't want to stop this thing unless it's absolutely essential.
Yeah, I can understand that. Say, I was out on deck when you fellas returned. Well, that is, when the firing party returned. What happened out there on Shot Island?
If you'll excuse me, I suggest you talk to Colonel Lunger about that. I have a timing signal coming up.
All right. So then, Dick, the firing party's big job is to see to last-minute details of arming and firing and to make sure that the Shot Island is secure.
That's the broad brush of it, yes.
I've been a member of firing parties before, but this was different somehow. A man standing, as I stood, on the outside of the building housing the mic device couldn't help but feel, to sense the importance of this moment. Inside, a handful of men were making a final check. Were arming a device which could be the key to a new era in atomic weaponeering. I don't know just how the others felt, but I felt small when I thought of the experiment being readied inside. This one test could take us out of the realm of kilotons into the fantastic world of megatons. And then, at H-6 hours, the job was finished. The mic device was on its own and ready. We all moved to take a final look at the gadget, which represents a year of intensive engineering. As we moved toward the pier, one couldn't get away from the feeling of being alone, of knowing you were the last to leave an island which might be shocked beyond human re-entry. We made the run from Shot Island down to the anchorage of the Estes off Perry in a fast crash boat. Soon after, the Estes made way through the deep entrance between Perry and Japtan Islands, out to a point 10 miles southeast of Perry, the rendezvous area of the task force ships.
We finished our job at the cab, came over the side, and here we are. Waiting on station just like everyone else.
Well, we won't have to wait much longer, Dick.
All right, thanks.
Well, that's part of the story. A small part, actually, of this whole ball of wax. An operation like Ivy has many facets, some large, some small. Behind the present activities on this ship, behind what went on at the atoll itself, whatever preparations had to be made in the States, is the broader story of policy, philosophy, of planning. Now, this deeper story, the background, so to speak, has its roots entwined in the broad international picture, in the larger aspects of the atomic weapons development program, in complex scientific conclusions. Not long ago at Los Alamos, I was talking to Dr. Alvin C. Graves, head of the test division there. He's on board now in Flag Plot as the scientific deputy to the task force commander. He's one of the men who can tell us about the thinking behind this operation.
And we're not really sure of what progress the Russians have made in this business of nuclear research. And so the only safe assumption to make is that they're interested in producing a fission bomb and to use it as some sort of trigger mechanism for a hydrogen bomb. It's obvious we don't want them to have a hydrogen bomb before we do. And so time is urgent. Time is the thing we have to beat.
Dr. Graves, the historical side of this operation is particularly important. I wonder if you'd mind speaking right to our camera.
Not at all. First, let's go over this business of the hydrogen bomb. Why use hydrogen? Hydrogen permits us to have an inexhaustible source of energy. It's plentiful. We don't have to worry about the critical mass limitation. Second, we can get hydrogen very cheaply. If we can use deuterium, we can distill it from ordinary seawater. We're floating on it right now.
That's very interesting, Doctor. But what is deuterium?
I was coming to that. First, let's consider ordinary hydrogen, such as is used commercially. An atom of this kind of hydrogen has the simplest nucleus known. It has one proton. But hydrogen exists in two other isotopic forms. Deuterium, which has a neutron in addition to the proton, and tritium, which has two neutrons and one proton. Ordinary hydrogen is not considered a good bomb fuel. And tritium, because of its expense and rarity, can only be used in limited quantities. Well, that's part of the background of Ivy leading up to the present.
In 1 minute, it will be H minus 45 minutes. H minus 45 minutes.
Silent deck for a bit.
All right, fine, Doctor.
Beginning to get light.
Quite a bit. Hi, Jerry. Worried about Mike?
Well, it's too late to worry about that now.
The Shot Island is about over there?
That's right. It's generally north and west of us. For the past half hour, the ship has been headed directly toward the Shot Island, and will continue to do so until shot time.
You know, there's one thing I can't quite put together. That's this business of success or failure. I've heard there's a 50% chance of its failing. Now, this low margin of success wasn't true on the other shots, was it?
No, it wasn't. Let me try out the Admiral's chair.
Sure.
Up until this operation, that is, from about 1945 through 1951, the chance of failure has never been more than about 10%. In Crossroads, Sandstone, and Greenhouse, we had great confidence in the operation succeeding. We recognized the change in philosophy, however, when Dr. Bradbury spoke to a group of us at Los Alamos in 1951.
Gentlemen, up to now, the laboratory has had sufficient time to compile information and revise weapon design before a field test of a weapon. As of now, the situation has changed. We must take risks. Calculated risks, it is true, but risks nevertheless. According to the presidential directive, we must ascertain if a hydrogen bomb is feasible and do this in the highest possible speed. We must ascertain if such a bomb is feasible, if we can, in 1952. Here is what I think we must do. We must set up a special staff under Dr. Marshall Holloway, reporting directly to my office. He will receive from the theoretical division the theoretical designs of such a system, have them fabricated, and shipped to Enowetok. There, they'll be taken by Dr. Graves and J Division and tested. It must be recognized that we're taking great chances, a great gamble, but a gamble, while there's a possibility of failure, nevertheless there's a possibility of great gains. Enowetok will become our theoretical laboratory rather than a proving ground.
And that's the way it is today. We're taking a gamble. I see that now. But then the uneasy state of the world puts everything on a gambling basis, I guess.
Yes, but not as much of a gamble as you might think. Take that man over there. He and his company have put a great deal of thought into the engineering and design of Mike. Well, see you later.
So long, Doctor, and thanks a lot. I couldn't help coming back to the control room for another look. They tell me everything's going along without a hitch. I've been taking a closer look at the cryogenic screens there. You know, there's a lot to this low temperature work. In a good many respects, it's the most outstanding problem of the entire operation. And as soon as Bob Gibney can break away, we'll talk about some of these problems. But this I know. A lot of heads have been scratched trying to figure out some way to work with various gases which have to be brought down to a liquid state. Oh, Bob, I've been browsing through this subject of low-temperature physics.
That's quite a subject.
It sure is.
The general problems connected with very low temperature operation had been met on the George shot of Greenhouse. The amount of thermonuclear fuel required for Mike's shot is considerable. Do you remember the buildings in the south end of Perry, near the airstrip?
Yes, I do, Bob.
Well, that's the liquefaction plant. The original plant was established during Greenhouse. Because of the difficulties in transporting, the decision was made to produce liquid hydrogen at Enowetok rather than in the States. But for Ivy, it had to be expanded considerably. The capacity of the original hydrogen plant was doubled for the production of liquid deuterium, and a new plant was built for the production of hydrogen with a capacity 4 times the old Greenhouse model. The small nitrogen plant was expanded 8 times its original size. For Operation Ivy, the Perry Island plant operated continuously for 3 months to produce the necessary low-temperature liquids needed in the experiment. But of course, you don't put a material so difficult to make and so difficult to keep in milk bottles. You use special containers called dewars, which are simply outsized thermos bottles. Months ago, these dewars were made in Massachusetts by the Cambridge Corporation and driven out to Boulder, Colorado for testing. Each dewar is mounted on its own truck with its own refrigeration plant and generator. Against the picturesque background of the Flatiron Range of the Colorado Rockies, these dewars were filled with liquid hydrogen at the cryogenics lab of the National Bureau of Standards. This plant, set in an unpopulated area, is the largest source of liquid hydrogen today, and hydrogen is essential for a practical shakedown test. The climax for these dewars came out here at Enowetok when they were actually used for the job intended, transport. Since production of thermonuclear fuels might be needed on future tests at Enowetok, it was thought best to put the liquefaction plant on Parry Island instead of on the shot island, where it probably would be destroyed. But this meant a satisfactory means of transporting liquid hydrogen from Parry to the shot island. This type of exaggerated thermos bottle mounted on wheels was the answer. A dewar is constructed to isolate the contents of the dewar from the outside temperature, so no heat can leak in. Contained within the boilerplate outer shell is an inner shell made of stainless steel with a vacuum in between. This is the container which holds the liquid hydrogen. A radiation shield made of copper surrounds the bottom half of the inner shell. There are two bottoms to the radiation shield, and in the space between them there is room for liquid nitrogen. The purpose of the radiation shield is to provide a barrier to the flow of heat. The heat which does leak in boils away the nitrogen first, thus protecting the liquid hydrogen. But even with all these precautions, another source of heat still occurs in the inner shell. This is mainly due to a special property of hydrogen. The molecules of hydrogen, as a gas, exist mainly in a state called the ortho. At first, when the gas is liquefied, the molecules stay in their original state. However, within a period of some 2 weeks, the molecules rearrange themselves into a state called the para. This is a natural phenomenon which always occurs. In this transfer, heat is given off, actually sufficient heat to boil off 2/3 of the liquid hydrogen. To take care of this excess heat, a special refrigerator has coils located in the inner shell. The refrigeration plant, which supplies these coils, does a remarkable job, for its coolant approaches absolute zero. Absolute zero, that unimaginably cold zone where everything stops. All life, all molecular motion. Minus 459 degrees Fahrenheit. A little above this fantastic figure, hydrogen becomes a liquid at minus 423 degrees Fahrenheit. This is the temperature to be maintained in the dewar. Only 36 degrees away from the bottom. Absolute zero. The helium refrigerant used can affect a temperature sufficiently low to cause the gaseous hydrogen boiling off to return to a liquid state.
Well, I went into more detail on the cryogenics end of this project than I intended.
Well, so far, we've pieced together quite a bit of this operation. I don't believe you have ever had a good look at our key test islands. The test islands for Mike are located at the top, or the northern sector, of Eniwetok Atoll, some 25 miles from Parry and Eniwetok, the two base islands of this atoll proving grounds. There are 3 main islands making up the test site. These are Elugelab, Teeter, and Bogan. Early in the game, these islands were linked together by causeways. The old business of men and machines digging and piling up coral sand. These connecting roads were built to make it easy to get from island to island, and also to act as land platforms for some of the instrumentation. A sizable camp was set up on Teeter. First, it housed construction people, and later served as an advanced base for scientists working on the shot island. In the early months, Elugelab was just another small, naked island of the atoll. But by midsummer, it began to look like the thing it was selected for, a shot island. Actually, the cab, so called because it houses the weapon, is not a cab at all, but a building set flush to the ground. It has all the earmarks of a common workshed, but in reality, it's a laboratory building set on a Pacific atoll.
How do we stand at Kwajalein?
Charlie?
Then they're all on the way except for the 3rd and 4th sample elements? Right. Are you picking them up on the scopes as they come into the area? Right. Yeah, well, from here in, let us have immediate notification if exact shot positions aren't maintained.
This is Broadway 3.
Yeah, and the helicopters, we expect to order them out in about...
Aerology, which may require you to move some of your units.
This, as you have probably gathered, is joint operations. All atomic test operations in the Pacific so far have been run under a joint task force kind of setup. Operation Ivy is using the